In this lecture, let us talk about the noise in AM system with carrier, and let us see how things will change. Again, we can intuitively expect how things should change. Now, we have two cases here. One is AM system, AM with carrier, and demodulate synchronously. Synchronous demodulation. You can ask me, why do we need synchronous demodulation for AM with carrier? It is useless, right? But still we will consider only for analysis purpose. In practical, in real life, we never use synchronous demodulation. See, we are sending the carrier to simplify the receiver, right? That is the sole purpose. We are sending the carrier along with the modulated signal. So in that case, we don't want a synchronous demodulation, but we want to compare the different systems. So we are considering synchronous demodulation. And the second one is demodulating with the envelope detector. Envelope detector. That's it. So first we will consider AM with the carrier and synchronous demodulation. Okay, here the carrier is not suppressed, that's what we mean by. So AM with carrier means it has carrier component explicitly. That means when you take Fourier transform, you will have an impulse function. So first let us talk about synchronous demodulation. Okay, it is also called coherent demodulation, because the receiver knows about the incoming carrier signal's frequency and its phase. So what kind of signal that you are transmitting now? You are transmitting the carrier with the modulated signal, double sideband suppressed carrier signal. So what is the kind of received signal? I can directly come to the received signal now. Okay, so my received signal is going to be √2 times A plus m of t times cos of omega c t. If you multiply this cos omega c t inside, then you will get dsBSE, and if you put here, then you will get carrier. See, if you multiply m of t times cos omega c t, what is this? This is the modulated signal. Let's say you put √2 here, plus √2 a times cos omega c t, and this is what? Carrier with carrier. So this is the transmitted signal. Transmitted signal also the same guy, √2 times a plus m of t cos omega c t. The same signal is received at the receiver, because we assumed the channel is an ideal channel. Now I have included a factor √2. Okay, this is included to make sure that the final signal power is simply SI. The message power is the same, just to simplify the algebraic manipulations, nothing else. Even if you don't put this √2, no problem, you will get the same result. Now let us try to find out what is the received signal power. This is my received signal. Now what is the received signal power? Okay, received signal is given, then you can find out received signal power. Let me denote by SI. So this is √2 times the whole square, then a plus, because after all it is m of t whole square and bar, that is expectation. by 2. So this is root 2 square becomes 2, 2 and 2 will get cancelled. So it is a plus m of t whole squared whole power 2. So if you expand this, this is equal to a squared plus m squared bar plus 2 times a times m of t. Now we already modeled our message signal as 0 mean wide sense stationary random process, right? M of t, your message signal M of t is modeled as 0 mean wide sense stationary random process. Now what about this guy? That is the mean of what? M of t. Therefore this becomes 0. So your signal input power to the demodulator is a square times m square bar. So if message is 0 mean, okay. So this means that message has no DC component, that's it, okay, because see, no one can speak in with a 0 frequency, right? The moment you start to speak, it has certain frequency, certain band of frequencies. So in that case, how can you speak nor how can you generate a voice signal with a 0 frequency? So that is not at all there. So this is your expression for the input power. So now the input power is no longer m square, because you are also transmitting the carrier. So that is why it is a square plus m square bar. In the previous cases and all, the input power is simply m square bar, but here it is no longer m square, it is a square plus m square. Now what is your demodulation process? Your signal root 2 times a plus m of t cos of omega ct is given to the envelope detector. Envelope detector means you have the multiplier. Again, let me put a root 2 times cos of omega ct. So this root 2 is simply for a constant, okay, to simplify the analysis. Even if you don't put that root 2, no problem, you will get the same result and put the output of filter. Now let me call this point as y1 of t and this is y0 of t. What is y1 of t? y1 of t is equal to this guy multiplied by with this guy. So root 2 becomes 2. Let me write down the result directly, or I can put a root 2 times a plus m of t cos omega ct times root 2 times cos of omega ct. Root 2 becomes 2 and then a plus m of t times cos square omega ct, then this is equal to 2 times a plus m of t multiplied by 1 plus cos of 2 omega ct whole divided by 2. This 2 and that 2 will get cancelled. So you will get a plus m of t plus a plus m of t multiplied by cos of 2 omega ct. This is my y1 of t. Now after you pass through the low pass filter, see this m of t is a low pass signal, no problem. Low pass signal. What about this one? It's a high frequency, okay, band pass signal. So that signal that will be removed by the low pass filter. So this will be rejected by the low pass filter. Therefore my output, detector output yd of t or y0 of t is equal to simply a plus m of t. Okay, so you are going to multiply the received signal with the root 2 times cos omega ct and the result will be given to the low pass filter. Okay, this operation is nothing but what? Demodulation, your synchronous demodulation after low pass filtering. And again, of course, this DC component also will be removed by the low pass filter. Therefore, your output y0 of t contains m of t. Okay, because a is not a message part is only the m of t. So even though this A comes out of the low pass filter, but my output signal part is not A. So as far as the signal part is concerned, I need to consider only m of t, no need to consider A. What is your output signal power? S naught is equal to m square of bar of t. So as far as the noise is concerned, what is n naught? N naught is again NB. Why is it NB? You have like this and here like this. The total bandwidth is, sorry, it is ideal band pass filter, right? And here also ideal band pass filter. What is the bandwidth? 2B, and here also 2B. This is centered at Fc and this is centered at minus Fc. Therefore 2B times n by 2, here also 2B times n by 2. The height is n by 2. So this is 2NB if you add these two guys together. Is it 2NB or NB? It should be 2NB, right? Where did I do the mistake? Let us see. One minute. Yeah, this is 2NB, but what is this noise? This noise is the output of the band pass filter. See, you have the signal here. I am right, you are right. Root 2 times A plus m of t times cos omega ct, right? Now here the noise is getting added. What is the noise? N of t. Now this is passed through the band pass filter. In this point I am getting Ni of t, narrow band noise. So the narrow band noise contains again Nc of t plus Ns of t. Sorry. That analysis I did not do, okay, because already we did this for single sideband modulation. So Nc of t cos of omega ct plus Ns of t times sin of omega ct. Now this one is, after this you have the demodulator. In the demodulator you have the product multiplier root 2 times cos of omega ct and then followed by low pass filter. Now what will happen? You multiply cos omega ct, so this term will go away, sin omega ct, and here this will becomes cos square omega ct. Cos square omega ct times Nc of t, then Nc of t times cos square omega ct becomes 1 plus cos of 2 omega ct by 2, and this 2 let us wait, by 2, then it will be Nc of by 2 plus Nc of 2 times cos 2 omega ct by 2, and you are multiplying by root 2, right? So that root 2 will come here, and here also that root 2 will comes. So root 2 and becomes Nc of t by root 2. Now what is the power of this? This is equal to 1 by 2 Nc square of t. Therefore 1 by 2, this Nc square of t is, we calculate this 2NB. Okay, so this is the power of Nc square bar of t. Okay. So 2NB, this 2, that 2 will get cancelled. This we already did, okay, that's why I did little fast here. NB. Therefore my output noise power N0 is equal to NB, and output signal power is m square of bar of t. What is S0 by N0? It is again m square bar of t divided by NB. What is this? This is our age old friend gamma. you can look at the process. How did I calculate this? So you have narrowband noise. This narrowband noise is multiplied by root 2 times cosine omega ct, right? You are multiplying by root 2 times cosine of omega ct. Then cosine omega ct with the sine omega ct becomes 0. I did not write that part here. And then cos times cos becomes cos square of omega ct. Cos square omega ct, I can write 1 plus cos 2 omega ct by 2, and here in the numerator I have root 2. Root 2 by 2 becomes 1 by root 2. So nc of t by root 2 plus this term will be eliminated by low pass filter because cos 2 omega ct. So finally you will get this one. What is the power of this guy? nc square of t divided by square of root 2, that is 2. Now this one we already know from this bandwidth calculation. From this figure we got it. That is equal to 2NB. 2NB. From the negative frequencies you will get NB power, and here we get a NB. Therefore it becomes 2NB. Okay, fine. S naught by N naught is equal to m square bar of t divided by NB. Now, but what is our input SI? I am sorry, I did a wrong thing. I am very sorry. This is not gamma. Gamma is different. Let us come to that. Okay, this is not gamma. This is what we got. And now what is our SI? SI is not m square bar of t. It is no longer m square bar of t. It is m square bar of t plus a. Therefore, it is m square bar of t divided by NB. You multiply both numerator and denominator by SI. Now rearrange this. SI by NB plus m square bar of t divided by SI. Okay, what is SI by NB? Now this is our friend gamma. What we did in the, what we got in the baseband communication systems, our benchmark. Okay, our benchmark gamma. Okay, times m square of t divided by SI. What is SI? SI is this guy. We calculated that m square of t plus a. Therefore, S naught by N naught in terms of gamma, our benchmark, in terms of benchmark is, let me simply write m square bar like this, divided by m square bar plus a. I am skipping the t here. Now this is the output signal to noise ratio of AM system with the carrier, and we did a synchronous demodulation. Okay, we didn't do envelope demodulation. It is synchronous demodulation. Now what do you infer from this? The output SNR is now smaller. Why? Because this m square plus a is the amplitude. So anyway, this whole thing will be less than 1. Okay, m square by m square plus a becomes less than 1. Therefore, your gamma is less than your baseband communication system. Therefore, the output SNR of your AM system is smaller than the output SNR of your baseband communication system. And that is expected. Why? Because you are transmitting an AM signal with carrier, and not the entire input power is useful in terms of message. Because what is my input power? SI is equal to A plus m square. This m square is my useful power. And what about this guy? Waste of power, useless power. Okay, part of this SI is carrier power and part of this SI is power in the message. Therefore, you lose in terms of performance. To get the same SNR as the other system like DSB, SC and then SSB system, you have to have a high value of gamma. Okay, because of this attenuation factor that is coming into the output SNR. If you increase the gamma value, then there is a chance. So obviously in terms of SNR performance, AM with carrier would be inferior. In terms of performance, AM with carrier inferior. Okay, now let us continue our discussion a little further to appreciate how much more power will be required in typical situations as compared to AM without carrier, that means DSBSC system. So let us consider the case, let us say the maximum value of the message is MP. M of t, the maximum value is M suffix p. So peak value of the message. Peak value of the message. Why that is so important? If you remember, typically you keep you would keep A plus M of t to be positive, right? Of course, for a synchronous demodulation that is not very important. But in AM system we said A plus M of t must be non-negative. Okay. For synchronous modulation this condition is not required, but for envelope detection this condition is required. Basically what it does is like A is greater than MP, maximum peak. Because if you have a negative peak, for example, A plus MP should still be positive, so the value of A should be greater than or equal to MP. So for maximum SNR, what should we do? To obtain the maximum possible SNR, I should choose A equal to the largest possible value of SNR. So the largest possible value of SNR will be your maximum peak value of your M of t. That gives the 100% modulation. So maximum SNR, because we said A plus M of t is greater than 0. Now let us say this is my speech signal like this, and this is my maximum value it can reach, my message signal. Let us say this is my MP. Therefore, in order to make this guy as positive, my A should be at least MP, maximum peak point, and let's say this is minus MP, negative peak, so that this quantity A plus M of t will be always non-negative. So that is the reason we are considering maximum SNR. Therefore, A is equal to MP. Substitute A is equal to MP in the above expression, and M of t is equal to MP. Then S naught by N naught maximum that you can achieve is M square bar divided by MP square bar plus M square bar. This is in terms of the peak value. Times gamma. Actually this was my A, so that A is replaced by MP square. In fact, if you write down very properly, then this is A square plus M square bar, and this becomes M square divided by A square. A square now becomes peak value MP squared plus M square bar times gamma. So this is some kind of expression for the output SNR in terms of only the message properties, nothing else. And you can also write you can take m square commonly outside, then it becomes 1 divided by 1 plus mp square divided by m square bar times gamma. So this is another way of writing the same expression. Now generally what will be this guy? See, the peak value power is always greater than m square bar, right, average power. So therefore this ratio, typically this mp square by m square will be more than 1. Okay, it will be more than 1 because mp denotes the peak value and m square bar is the mean square value. So mp square bar divided by m square bar is greater than 1. So obviously the denominator is greater than 1. Okay, so let us assume this is equal to 1, then at the most let us assume 1. Therefore 1 divided by 1 plus, let's say this also 1 times gamma. So therefore I will get some kind of upper bound less than or equal to gamma by 2. Therefore S naught by N naught maximum is less than or equal to gamma by 2. This is of course a very rough bound, but what this bound tells you is that at least 3 dB disadvantage or 3 dB cost associated with the use of carrier than not using the carrier. If you don't use the carrier, then S naught by N naught is equal to gamma. If you use the carrier, then its performance is reduced by half. So you have the 3 dB disadvantage. or 3 dB cost associated with the use of the carrier, then not using the carrier. That means I must require at least 3 dB more power, twice as much power for transmission. That means gamma should be at least twice as much as earlier, so as to get the same value of SNR. Typical situations will be actually more than 3 dB in reality, because this MP by m square bar will rarely have equal to 1, because here we assumed this mp square by m square bar is equal to 1, but this is a very rare condition. Okay, so just 1 minute, I will be back. So therefore 3 dB disadvantage with carrier. So depending on the actual value of this ratio, your mp square by m square bar, actual value of this ratio, actual SNR reduction or SNR cost, that means the power cost associated with the use of AM with the carrier is more than 3 dB. So typical figures are more than 6 dB to 9 dB loss. Okay, so there is 6 dB to 9 dB loss in power efficiency in your AM with carrier. This is expected because of the transmission of your carrier. For example, suppose your modulating signal was a sinusoid. Just for the sake of discussion, what is the peak to RMS value for that? Peak to RMS value is root 2. That means MP by M square bar is equal to root 2 the whole square, which is 2. So instead of mp square by m square bar is equal to 1, we have mp squared by m squared bar is equal to 2 now. In this case, what will happen? In the numerator 1, in the denominator 1 plus 2 times gamma, this is gamma by 3. So look at the previous expression. Yeah, 1 divided by 1 plus mp square by this one m square bar. So I substitute in that expression. So S naught by N naught maximum for sinusoidal signal is equal to gamma by 3. So gamma by 3 you can write gamma minus in terms of dB, for gamma suffix dB, let's say S naught by N naught maximum for sinusoidal signal in terms of dB is equal to gamma in dB minus, if you take log, if you convert 3 in terms of dB, then it is 4.77 dB. So you require 4.77 dB more SNR to get the same output SNR of your DSB-SC system in the case of sinusoidal modulating signal. At the input you require this much extra power to get the same output SNR. So 3 dB is the minimum value. Actually it ranges somewhere between 6 dB to, where did I write? Yeah, 6 dB to 9 dB. So what you learned is that there is a cost associated with the performance or power efficiency when you transmit the carrier. Of course, the reason why we do it is because it is simpler to demodulate. Okay, we don't actually have the synchronous demodulator. So AM with carrier, whenever we are doing, then we generally don't use synchronous demodulation. Why? Synchronous demodulation is very complex. Not very complex, it is complex. So instead of that, you can simply take a diode and followed by a capacitor and followed by a resistor, and simply can demodulate it. So this is my envelope detector. So the reason why we transmit carrier along with your modulated signal is to simplify the receiver structure. I mean simplify the demodulator. Therefore, the output SNR that you have calculated is for the situation where the demodulation is synchronous. Okay, so as I said, actually we transmit carrier so as to get the simplicity of the demodulation, not to have to use synchronous demodulation. So the next question is, would the envelope detector give you the same performance as the synchronous detector does, or as the coherent detector does? That is the next question we are going to look at. Now let us look at AM with the envelope detector. Okay, let me discuss this in the next lecture. Thank you very much.